The next person who's speaking, I'm kind of a little excited and smitten by because he used to be the Deputy Chief Technology Officer for the United States. So we have someone coming from politics, that's my old stomping ground. Edward Felten, now with Offchain Labs. He's going to talk with us, as you can see, about trustless, scalable smart contracts. Take it away, and if you want this mic.
Let me try this one and see how it goes. All right. Hey, everybody. So I'm Ed. I'm the co-founder and chief scientist at Offchain Labs, and I'm going to talk about Arbitrum Rollup. This is the first Rollup product that is available on testnet for general smart contracts. So first of all, some background, what is Rollup? There's different Rollup systems that have been proposed, but basically, I would say Rollup is characterized by three things. First, it's an approach where you build a scalable layer 2 chain that's anchored on a small layer 1 contract. By building on top of that small layer 1 contract, you can get the security of a layer 1 solution, but the scalability that you get by moving a lot of stuff off into layer 2. In particular, computation and data moves off-chain. The second thing about Rollup is that you post as on-chain call data everything that's needed to follow and validate the correctness of the L2 chain. So everyone who wants to can follow what's happening on the L2 chain, reconstruct it all, and figure out if it's correct. And that means that you have the ability to participate in the protocol to ensure correctness at L2. So that's all transaction calls and data hashes of the contract state and of outputs. And the third thing that makes Rollup is that you advance the L2 chain by posting a Rollup block to the L1 chain. That includes the results of multiple L2 calls that you post all rolled up into a single transaction to make it cheaper. The system, of course, needs to validate those Rollup blocks somehow, and that's where a lot of the secret sauce is. Okay, so let me talk about Arbitrum Rollup. Arbitrum Rollup is a Rollup approach that is our product. It supports general smart contracts. We compile your code from Solidity, so you don't need to modify your code except in the slightest way. It's compatible with standard front ends, so we offer plugins for Web3, Ethers, and Go Ethereum, so that you don't need to rewrite your front end. The user can use the same browser-based front end that they want, working with MetaMask or a standard wallet, and you just have to change a few lines in the initialization of your front-end code in order to pull in our plugin. We provide easy tooling for launching a chain for your dApp. We're not a single chain. We're a tool for launching many chains, and we anticipate one chain per dApp. That gives better control and better performance for each dApp. We provide easy tooling for launching a chain, moving ETH in and tokens in and out. We grew out of Princeton University research, and we're the first Rollup for general contracts to be available and working on testnet. So, if you want to launch an Arbitrum Rollup chain for your dApp, let me talk about how that works. And I'm going to do two things for most of the rest of my time. I'm going to talk first about what is the developer experience, what do you have to do as a developer to actually use this, and I'll occasionally stop and we'll go under the hood and talk about how it works and why it's designed the way it is. Okay, so you want to launch. The first thing you need to do is compile your dApp. So your dApp may consist of a bunch of Solidity code, maybe a bunch of contracts, a bunch of libraries, a pile of .sol files, and some migration stuff. You take all of that and you feed it into the Arbitrum compiler. The Arbitrum compiler takes those different pieces that make up your dApp and it crunches them all together into a single executable file we call an Arbitrum executable, which might have a name like mychain.ao. And that is a thing that you can then launch as an Arbitrum chain. So you do that by using a command line like the one on the upper right, truffle migrate -- network Arbitrum. We have a plugin for Truffle that makes it just that easy to compile your existing Solidity dApp to run on Arbitrum. And that takes care of everything to make this one file, that mychain.io. Now, when you do this compilation, we also include into your executable a few other things. We include, first of all, the Arbitrum token bridge. This is a mechanism for easily moving ETH and ERC20 and ERC721 tokens in and out. So a user can transfer tokens, deposit tokens into your chain. They can withdraw tokens from your chain, and we provide the contract and protocol support for that automatically. We'll link it in with your contract automatically, and we provide a nice front end that I'm going to show you later for that functionality. We also provide, compiled into your code, a bunch of bookkeeping, dispatching, and management services. And the reason we do that, basically, is that some other solutions will do a certain amount of bookkeeping and management on-chain in the L1, in the master L1 contract. But we found that by moving some of those functions into L2, we can operate them at the efficiency and at the low cost of L2. So we take as much as possible of the bookkeeping and management and all of that kind of stuff needed to operate a chain, and we move it actually into the L2 itself. And we compile that in automatically into your Arbitrum executable. So that's a single package, a single file that you can launch. How do you launch it? Well, you go to this URL, which you can't quite read up there, but it's developer.offchainlabs.com/tools/deployment, and you get this form. So up near the top, you see there's under contract upload, there's a box, and you can drag and drop one of those .ao files into that box, or you just click the box, you get a file chooser. It's that easy to inject your .ao file and to get it set up to start a chain. Down in the bottom, there's a bunch of parameters for your chain you can set. We have presets. Here I've clicked the preset for local testing. When I just click that preset, I get parameter values that we suggest to use for local testing. So having dragged my .ao file in, having clicked that preset, I then click the button at the bottom, create rollup chain, and now I've made an Arbitrum rollup chain. This calls an on-chain contract called the Arbitrum Chain Factory, and it launches your chain. Your chain is now up and running as an Arbitrum chain. Okay, let me now stop and go under the hood and talk a little bit about what is actually happening while your Arbitrum chain is running. I apologize for the flickering. So down at the bottom, you have the Arbitrum chain. And in running your L2 chain, there are two Ethereum contracts that are involved. There's the Arbitrum inbox contract and your chain's Arb Rollup contract. The inbox contract is responsible for intake. Whenever a client makes a call to your chain, whether it's making a transaction call to one of your contracts, depositing some ETH or some tokens or something like that, they do that by calling the inbox contract, and the inbox contract manages those incoming calls, keeps a list of them, and so on. Everything else needed to run your chain is done by your chain's Arb Rollup contract. That keeps track of the state of your chain, and it makes sure that everything is recorded and everything is going to execute correctly. The workhorses of your Arbitrum Rollup chain are validators. Validators a validator is a program that can run anywhere. If you are the dApp developer, you might run a validator or two. You might use a validator as a service company. We're talking to infrastructure providers about providing validation as a service, and you should expect an interesting announcement along those lines very soon. But anyone else who wants to function as a validator can do it. They can download the free source code from our website, or they can download a Docker image and run it, just start it up, and they will operate as a validator. And the guarantee that we give is that as long as any one validator is honest, the chain will execute correctly. So more validators is only better. That's just more people who would have to all be dishonest in order for something to go wrong. So whoever starts up validators starts up those validators. Those validators are responsible for pushing the state of the chain forward and for calling each other out if some other validator is lying. So the validators interact with those on-chain contracts in the normal way. Every validator interacts with the inbox contract they watch the inbox contract in order to see incoming requests, and they interact with the Arb Rollup protocol to do stuff that I'm going to show you in a few minutes to push the chain forward. If you have a user who's operating with, let's say, a browser-based front end using Web3 or Ethers and our plugin, the user's sitting at their browser, the user does a thing in which your front end wants to make a call. What that does is that the user's browser will then make a call to a transaction call message to the Arbitrum inbox contract to deposit that transaction call into the inbox. If there's a payment that goes along with it, that will be recorded, and everything else that you'd expect for a transaction call. So the front-end code in the user's software doesn't know that it's calling to an L2 contract and not to L1. The plugin takes care of bridging that gap. But what happens is then a TX call message gets sent to the Arbitrum inbox contract, and it shows up in the inbox. The front end, again, also through the plugins which we write and provide, interacts by remote procedure call with one or more validators in order to find out what's going on the chain, in order to ask for other things, and to see events that happen on the chain. So those are the pieces that are interacting. And we provide the code for all of these things, except, of course, the application-specific parts of the front end. OK, so let me talk about the inbox contract. Every Arbitrum Rollup chain has an inbox which holds a sequence of messages from clients to the L2 contracts. There are different message types, transaction call, a token deposit, stuff like that. The messages are ordered in the inbox, and they're time-stamped with the main chain block number when they arrived, so that the L2 contract can ask, by calling an Arbitrum library, when was this thing put in, when was this thing submitted, if it wants to. The contents of these messages are posted on-chain as call data, so anyone who wants to see them, such as a new validator who comes along, can see them. The on-chain inbox contract doesn't actually store this stuff. It just maintains a hash accumulator of the inbox contents. That's enough for it to validate claims that other people make later about that certain things were in the inbox. And so the work that this inbox contract has to do is quite small. The way that the rest of the operation of the chain, or at least the link to the L1 chain, is done by the Arb Rollup contract, of which there's one separate one for each of your chains. So the way that the system makes progress here is through what we call assertions, which other similar systems might call a rollup block. The idea is any validator can post on-chain an assertion. This is a claim about what the chain did or what the chain will do, which is really a claim about what the contracts in the chain will do. That assertion involves the chain consuming some messages from the head of the inbox. Those are, say, the transaction calls that are going to get executed by the contracts during that assertion. It says that the contracts execute some number of steps of computation in the chain's virtual machine. It says it updates the chain's root state hash. The entire state of the chain is represented as a giant Merkle tree. And so there's a root hash, which is a commitment to the entire state of the chain. And that's part of the assertion. What is the state hash after this computation has happened? And then also some outputs that were produced by the contracts, things like log items and payments that were made. So all that stuff is asserted on-chain, and the Arbitrum protocol is going to decide whether to accept that assertion as valid and confirm it, or whether to reject it. So how does that accept or reject work? In order to get into that, I need to talk a little bit about some of the data structures inside the operation of the chain, in particular this thing we call the state tree. So here we have a state in the history of an Arbitrum Rollup chain. Each of these boxes represents a particular state in the history of the chain. And all of this history is confirmed, which means it's final, it definitely happened, the chain has decided, it's accepted. And so the chain keeps track of the latest confirmed state, or actually just the hash of it. Now, at some point, a validator, Alice, might decide to make an assertion, a claim that the next thing the chain will do is whatever. When Alice makes an assertion, basically that forks the tree. It forks the possible future histories. There's one future state if that assertion is accepted, and another one if it's rejected. And the system is going to decide which of those boxes to move to. Now, when Alice makes that assertion, she's required to stake on the node at the top there. And when she stakes on the node, she is saying that she is putting her money behind the claim that that state is correct. If that state is eventually confirmed, she'll get her stake back. If it's rejected, she'll lose her stake. So she has money at stake in doing this. Now, when Alice makes this assertion, she's claiming the state will be confirmed. A timer starts. And this is the period in which other validators have to check out Alice's assertion and to challenge it if they think it's wrong. OK, so Now, Bob might come along. He might also stake on that outcome. He's allowed to do that. He's putting his money where his mouth is. He wants to make sure that Alice's assertion gets accepted. Now, if you have a situation like this and the timer expires, the deadline is passed, everyone is staked on the upper branch, and so the system says nobody disagrees. They've had their timeout in which to disagree, and so that upper branch will be confirmed. But the other thing that could happen is some malicious or confused validator might come along before the deadline and stake on the bottom branch. Now you have a dispute. Now Alice and the malicious validator get into a dispute, and the Arbitrum dispute resolution protocol will be triggered. And the dispute resolution protocol will efficiently figure out whether Alice is lying or the malicious validator is lying. In this case, Alice is telling the truth, so Alice will win the dispute. When Alice wins the dispute, the malicious guy's stake is taken. Half of it is given to Alice, half is burned. The malicious guy is kicked out, and now you have a situation like this, and now the system is happy to accept the top node because there's no dispute anymore. So if there is a dispute, the people will fight it out, cage match style. Somebody will be left standing. If you are correct, you can always win these disputes, and so you can force acceptance of the correct branch. Okay. The other thing you need to know is that in order to make this fast, we allow pipelining. What that means is that while Alice's assertion is still under consideration, Bob can come along and make a claim about what comes next, building on top of Alice's node. He has to stake on that, of course. You always have to stake on your assertion. So now notice that Bob is staking on his claim, but he's also implicitly staking on Alice's claim. Because if Alice's box is not accepted, then Bob's definitely won't be, and he'll definitely lose his stake. So Bob is staking on both of those. Alice might then make yet another branch like this, and this is what it typically looks like actually in operation. The tree typically looks like this. This pipelining allows the system to keep going, so you don't have to stop the world and wait for the timeouts whenever there's the possibility, whenever you need to wait to find out whether somebody will dispute something. This ensures the chain can go at full speed no matter what. Okay, so we can make progress even if the deadlines are long, even if there are disputes, we keep making progress. The honest validators can always keep building out the correct branch. Dishonest validators are going to lose their stake. Whatever they've built will be pruned away, and progress will continue. Now, you might think all of these nodes and branching and stakers and so on are expensive to track on-chain, but there are tricks for reducing how much we have to store. Turns out the on-chain contract just needs to keep track of the hash of the latest confirmed state, the hash of every leaf of the tree. In that previous diagram, there were 4 of those, and also for each staker, who the staker is and the hash of the state they're staked on. That's all that needs to be tracked, so that's actually pretty small. The rest of it can be proven or checked as necessary from those hashes. When there's a dispute, there's a separate contract that's spawned for that when needed. We don't worry too much about the cost of that because the malicious party is going to lose a giant stake, and that is going to pay for dealing with that contract. Now, dispute resolution is very efficient. It uses a bisection-based protocol. If you've seen past Arbitrum talks, you've probably seen stuff about that. So this protocol gives you some really nice properties. It gives you trustless correctness and progress. Trustless correctness means that if any one validator is honest, the system will never go wrong. Any one honest party can stake on the correct outcome. They can win every dispute, kill off everybody who's wrong, and take their stakes, and then the correct thing will survive. So any one honest validator, and that can be you if you're concerned about it, can ensure correctness. Also, trustless progress. Malicious parties cannot stop progress. They can't stop the building out of the correct chain. They can't stop themselves from getting killed off in disputes, and so they can't stop the confirmation of correct nodes. So any one honest guy can force progress. We also provide trustless finality. So most of the states updates that are made are going to be confirmed as soon as their deadline is reached. If nobody's malicious, that's what's going to happen. We expect the deadlines in production to be measured in hours. If there's a dispute, the confirmation of that node has to wait for a multi-round dispute protocol, so the withdrawals at that point might be delayed for a day or two, but the chain still makes progress, and as soon as the dispute is cleared, the chain will catch up. And you'll be able to confirm all the things that were waiting on that dispute. We also provide the trustless finality guarantee, which is that if an honest staker is staked on some future state, that future state definitely will be confirmed eventually. That means that if you want to borrow against a withdrawal that you know will be confirmed eventually, you can borrow from that on a staker, or if you stake on a future where your withdrawal is recognized, you know that withdrawal will happen. And that's also a really important guarantee. So people can provide early guarantees of finality, early payout, or advancing of funds against withdrawals because they can force those withdrawals to definitely happen. So the summary here, the Rollup protocol moves computation and storage off-chain. The design is optimized for a high speed limit. We provide trustlessly correctness, progress, and finality. There's tooling for easily supporting Solidity dApps and standard front ends. We have tooling for launching chains, moving ETH and tokens in and out, and so on. Okay, so you can try this today. It's on beta, it's running on testnet, and if you go to our developer.offchainlabs.com, you can see all of our documentation. Okay. Now let me show you a demo, and I'm not going to do the demo live because live demos and 15-second block times do not go well together. So I'm going to show you screenshots we took a few minutes ago upstairs. Okay, so this is the Arbitrum token bridge, so you can launch this UI for any Arbitrum chain, and you can see what it has in it. It has tabs for ETH, ERC20, and ERC721. You can put in here, I've put in some ERC20 token, which I want to deposit into the chain. I can do the standard operations, approve, deposit into the chain. I can withdraw from my account on the chain through this UI. And I can, when I withdraw, it goes into a lockbox, and I can then do another click to withdraw from the on-chain lockbox. So all of this is provided for every chain. And because these things are put in the inbox, and the inbox is guaranteed to be processed in order, your withdrawal will be processed in order. That's true for every chain by design. Okay, so I can do this. I can deposit into my demo chain some ETH and an ERC20 token or two. Now I can launch my my demo dApp. This is Uniswap running on Arbitrum Rollup. We have it running upstairs, and these are screenshots we took a few minutes ago. So we launched this thing, Uniswap, running on Arbitrum Rollup. I previously deposited into this chain some ETH and some ERC20, and I can go through the standard Uniswap front end. This is an open source front end that we got online. So for example, I can create a Uniswap exchange. By filling out the normal forms. It gives me, I put in the address of the ERC20 token I want to use, click the Create Exchange button, and I can go on with, right, so I can create that exchange, and I can go on with the other steps. I create the exchange, I can put liquidity in, I can put in liquidity in the form of ETH and the ERC20. I can do transfers. I can buy and sell in the Uniswap contract. If you want to see this running live, come on up to our booth upstairs, Offchain Labs, and this is an example of the kind of dApp you can run. It took one of our developers a fraction of a day to get this working. It was not a huge porting load. You can talk to the guy who did it, again, upstairs, if you want to know how it works. So this is a demo that you can run real dApps that people actually care about as an L2 chain fairly easily. So that is Arbitrum Rollup. I'd be happy to take any questions if we have time, and until the MC interrupts us, I will take questions. Yes? Yeah. How do we prevent nefarious validators from front-running by publishing to the main chain? When clients make a call to the chain, that call does not go through the validators. That call is made directly to an on-chain Ethereum contract, to the inbox contract. The reason the inbox contract is there is so that clients can speak directly to the Ethereum chain to put their request in, and those are guaranteed to be executed in order. So there are people who can front run you on the Ethereum chain, and we can't stop that. But the validators are not in any special position to front run anybody. they have to execute those calls in the order that they were put into the inbox. And so the validators don't get the ability to reorder or anything like that. That censorship resistance is a really important property, and that's why we decided to have an on-chain contract to process incoming calls, just to record incoming calls. Oh, so the question is, can you see what's coming? So here's the thing. You as an observer know everything that the validators know about the state of the machine and what's in its inbox. And so if you want to follow along, or if you want to be a validator, you can do that. You can keep exactly up to date. You can even compute ahead and say, well, the next 5 things in the inbox, here's what they are. I can figure out what the chain is, what the contracts are going to do. So the validators have no advantage over Joe Public in figuring out what's going to happen. And so we don't think they're in an advantageous position to front run. Yes? So in the current implementation, it's a per chain, it is a per chain parameter how much the stake is. And all validators stake the same amount. There are a bunch of ways in which you might want that to vary. One way is you might want it to go up and down as the number of funds deposited in the chain changes. There's no fundamental reason we couldn't do that, but we don't do that in the current version. We also currently support staking only in ETH, but we expect pretty soon to support staking in ERC20s as well. There's no fundamental reason not to do that. The point of the stake is to deter bad behavior, and as long as there is enough stuff of value that is staked and the other validators find that stuff to be of value. So we want validators to fear losing their stake, and we want validators to want to get into a dispute with the liar in order to take their stake, right? And so as long as it's something that the validators value, then you can stake in it.
Probably just one more question.
One more question. Neil. How long till we launch on mainnet? We just launched in beta earlier this week. And the road to mainnet is addition of some features, probably nothing really major, but the main factor is security due diligence. Before we tell people you can trust your real money to this, we need to do more security due diligence. And that'll take as long as it takes. We think it's measured in months.